So now let's discuss about the energy fluctuations in canonical ensemble, or it's otherwise it can be considered as the equivalence between the canonical and the microcanonical ensemble. So far from our discussion of the ensemble formalism, we have seen that we considered certain examples like classical ideal gas. So the example of classical ideal gas were discussed using microcanonical ensemble, and later by using canonical ensemble. And the outcome was that at the end of the discussion, we were able to arrive at the familiar equation of state for ideal gases, that is PV equal to nRT. So the equation of ideal gas could be derived by considering our system either as a member of the microcanonical ensemble or as a member of the canonical ensemble. While discussing those ensemble formalisms, I had mentioned that both the approaches, approach and the microcanonical approach, will give you the same result in the thermodynamic limit. Okay, hope you remember what is meant by thermodynamic limit. It's the limit where the number of particles in a system tends to infinity, the volume available to the particles of the system also tending to infinity, keeping the number density of particle n by v as predefined or pre-assigned fixed value. So it establishes the fact that the canonical and the microcanonical ensembles will be equivalent in the thermodynamic limit, and we will establish that fact particular lecture. So in the canonical ensemble, a system can have energy anywhere between 0 and infinity. You know, the canonical ensemble, the macro state variables of the system are n, v and t. So it means that the energy can have any value that is varying between 0 and infinity theoretically, 0 to infinity theoretically. Okay, and in the microcanonical ensemble, we have seen that the energy is restricted to a very narrow. So the energy of the system will be between some value E minus delta by 2 and E plus delta by 2. I can say H. Okay, E plus delta by 2. So we have seen that the energy does not fluctuate much in the case of microcanonical ensemble, whereas energy is permitted to vary or fluctuate between 0 and any maximum value, say infinity, in the case of a system in canonical ensemble. Now we will we will just compare and see that even though theoretically the energy can fluctuate between 0 and infinity for a system in canonical ensemble, how far the fluctuation will occur in that system. So we are going to see that. അപ്പോൾ നമ്മൾ കണ്ടു എന്താണ് ഒരു കാനോണിക്കൽ എൻസംബിളിലെ മെമ്പറായ ഒരു സിസ്റ്റത്തിന്റെ എനർജി സീറോയ്ക്കും ഇൻഫിനിറ്റിയുടെ ഇടയ്ക്കുള്ള ഏതൊരു വാല്യൂവിലും ഫ്ലക്ച്വേറ്റ് ചെയ്യാൻ അതിനുള്ള ഫ്രീഡം ഉണ്ട്. പക്ഷേ പ്രാക്ടിക്കലി നമ്മൾ നോക്കുമ്പോൾ നിങ്ങൾ കാണും, ദാറ്റ്സ് വാട്ട് വി ആർ ഗോയിങ് ടു എസ്റ്റാബ്ലിഷ്, ദിസ് എനർജി ഫ്ലക്ച്വേഷൻ will be very very less. It is infinitesimal എന്ന് നമ്മൾ പ്രൂവ് ചെയ്യും, even though we permitted that one. So in order to do that, what we are going to do, we are going to calculate the root mean square fluctuation in the energy. You know, we are employing a statistical method, and in statistical methods we calculate the fluctuations or variations by some statistical quantities like standard deviation or mean square fluctuation or root mean square fluctuation, etc. So in this topic we will be calculating the relative root mean square fluctuation in the energy of a system in canonical ensemble, and we will prove that this fluctuation is negligibly small. Okay, or the conclusion follows that the energy, even though it is allowed to fluctuate between 0 and infinity, practically the energy fluctuation is very very small, so that the results obtained regarding a system in microcanonical ensemble is almost the same as what that result obtained in canonical ensemble. Okay, so let's begin with. So in order to begin, let me first define how do you calculate how the mean square fluctuations in the case of any physical quantity statistically. So let's consider a physical quantity, say F. So I'm considering any physical quantity. Consider a quantity a physical quantity. It means any measurable quantity that you can measure statistically. Any physical quantity, say let's call it as F quantity, say F, and we need to understand instantaneous fluctuation in the quantity. So therefore the instantaneous it's going on fluctuating, and the value takes different magnitudes with the passage of time. So instantaneous fluctuation, you know, fluctuation means it is changing. Okay, instantaneous fluctuation in F, in the quantity F can be energy, F can be the position, F can be the entropy, whatever it is. Okay, it can be any physical quantity that is thermodynamically defined. So instantaneous fluctuation in the energy or in the quantity F is defined as delta F. So instantaneous fluctuation is defined as delta F. So delta F can be understood as the instantaneous value. It's the difference between instantaneous value and the average value. So the quantity will be having an average value, average over some time, okay, and it will have some instantaneous value. So that is a change in that value will be equal to instantaneous value minus average value. Okay, so I can represent it symbolically as instantaneous value. I'm calling it as AF, okay, minus the average value. I'm going to represent it as by this symbol, right? The angular bracket of F. Delta F is equal to, this is the definition of instantaneous fluctuation in F. Okay, so let me take the square of this fluctuation, so it will become delta F square. So it is known as the square of fluctuation. Okay, that will be equal to, of course, I have to square the right side. So F minus, okay, the average value of F, the square. Okay, just a moment. Yes, so that is F minus F the square, which you can obtain. The value will be okay. Of course, you can just write that is equal to A square, that is F square, plus B square means what? It will be yes. So this is that of F square, then minus 2AB, minus 2 into, okay, minus 2 into F into F, right? So that is what you're going to get. Now what you got right now is the square of fluctuation. Let me take the mean. So I'm taking the mean of this quantity. Mean means average, no? Taking mean, I'll be getting what is known as the mean square fluctuation. So I have to take the mean on left side and the right side. So taking mean on the left side, it will be mean of delta F square. This is known as mean square fluctuation in F. Okay, so I have to take the mean of each term on the right side. So what are we thinking? It will be mean of F square. Okay, so there is an angular bracket denotes actually the mean or the average, right? So mean of F square plus, already see the second term, the mean has been taken. So mean means it's a single value, and when you take the mean of a single value, you'll be getting the same value only. So I'm repeating the same thing as mean of F the square. Okay, mean of F the square minus, see, note the difference. First one is the mean of F square and second one is mean of F the square. It will be a single value. Okay, so it is not affected by taking mean again. So minus 2 is a constant, then F is again I have to take the F is a fluctuating instantaneous value. So there is F into, then already there is an F there. So already the mean is taken, means it's a single value, it's not affected by taking again mean. So that's why I'm retaining it. So this is the thing what you're going to get. Now can you see that this one is nothing but you can just see that this is nothing but mean of F square plus mean F square minus 2 into mean of is again mean of square, right? So that is mean F square. So you can just simplify this one. This is nothing but equal to mean of F square minus mean F square. See, that is what is known as the we call it as the mean square fluctuation in F. So we call this one as some equation number 1 to begin with. So equation 1, this one represents the mean square fluctuation in F. So before we proceed, let me ask you, why do we go for something like mean square fluctuation in F? Statistically, what is the physical concept? What is the motivation behind finding out the mean square fluctuation of a quantity? Why don't you get satisfied with the fluctuation or mean fluctuation, to be precise? Why do you go for a square of the fluctuation and then take its mean? You know, that's the same principle that we have been using whenever we are considering quantities like RMS values, right? You are used to finding the RMS value of velocities, RMS value of current, etc. Whenever the quantities are fluctuating, we are supposed to take the root mean square values. Okay, why do we do that? The reason should be
or system. I hope that idea is clear to you. Okay, fine. So anyway, what we need here is only equation number 1. So then we will apply equation number 1 for our real system now. And instead of F, in our case, in place of the quantity F, we are going to consider that is internal energy U. And so our purpose is to find out what is the fluctuation in energy. And so we will calculate the mean square fluctuation in energy, okay, for a system in canonical ensemble. Let's see how to proceed. So for that, we first need the average energy of the system, right? So the in canonical ensemble, so let's first write down. In canonical ensemble, the average energy, average energy of the system, average energy of the system is regarded as the internal energy of the system in canonical ensemble. average energy of average, okay, of a system, average or mean, okay, that is given by, that is considered as the internal energy U is equal to the average value of the energy of the system, and average of any quantity E is given by sum over R ERPR. Okay, hope you remember this relation we have used already. Average energy, relevance of significance of statistical quantities. Okay, we have discussed the mean value of energy is equal to sum over R ERPR, or where PR is the probability. So you can substitute for PR. PR is the nothing but the Boltzmann's probability factor. So that will be equal to sum over R ER into PR is equal to E raised to minus beta ER divided by, what is that divided by sum over R E raised to minus beta ER. And you hope you remember, still the denominator was nothing but the canonical partition function for a discrete system, right? So let me say that this is my equation number 2. So that gives you the mean energy. Now you have to find out mean square fluctuation, right? So for that, taking square. So taking square, I want to take the this is a thing. So taking square, what I'm going to get. So this is square of that value. Taking square, that is square of this quantity. See, that will be equal to, I can just write as such. So that is sum over R e raised to minus beta. There should be an ER now. Okay, I can write that ER first. ER sum over R ER into PR. So that is ER e raised to minus beta ER divided by sum over R e raised to minus beta ER. Always remember the denominator is representing the partition function. Okay, so that whole square, that is, let me call this one as some 3A. Okay, so you got this one. Similarly, I want another thing. You need this quantity and square of the mean of the square. Okay, square of the mean and mean of the square. So we have already found out square of the square of that quantity. So we have to just take the other one. So the mean of the square of that quantity. So mean of the square of the quantity, that is, and I can continue. What will be the mean of E square? So you note the difference between the two. Mean of E square. So first you have to find out what is mean of E given by. Mean of E is given by this equation. So E is the physical quantity, and mean of E is equal to sum over R. That quantity what you are trying to find out, whose mean you are trying to find out. ഏത് ക്വാണ്ടിറ്റിയുടെയാണോ മീൻ കണ്ടുപിടിക്കേണ്ടത് ആ ക്വാണ്ടിറ്റി summation over PR. Multiply by PR. That's what you do. So ഇവിടെ നമുക്ക് E സ്ക്വയറിന്റെ ആണ് മീൻ കണ്ടുപിടിക്കേണ്ടതെങ്കിൽ അതിന്റെ ഇക്വേഷൻ എന്താ വരിക നമുക്ക് കണ്ടുപിടിക്കാൻ പറ്റും. That is equal to sum over R. E സ്ക്വയറിന്റെ മീൻ ആയതുകൊണ്ട് നമ്മൾ എടുക്കേണ്ടി വരിക എന്താണ്, ER സ്ക്വയർ എന്നിട്ട് അതിനെ മൾട്ടിപ്ലൈ ബൈ PR എന്ന് വരിക. ഓക്കെ, അപ്പോൾ നിങ്ങൾ ഓർത്തുക ഏതൊരു ക്വാണ്ടിറ്റിയുടെ ആണോ മീൻ കണ്ടുപിടിക്കേണ്ടത്. Okay, suppose you have to find out the mean of M, then the equation will be sum over R MR PR. Okay, suppose you have to find out the mean of M square, then the equation will be sum over R MR square PR. So you have to multiply by PR in order to calculate the mean of the quantity. So that is the statistical method of finding out see the mean of the quantities using such equations. So this one is ER square into PR. So ER square into PR means I can substitute for this one. So that is equal to sum over R ER square. I'm writing ER square. PR, you know what is PR equal to? E raised to minus beta ER. PR, you have the standard equation, divided by sum over R E raised to minus beta ER, which is the Q. So we call this equation as 3B. See, look at equation 3A and 3B. It seems quite similar, but there are differences. You note it. Okay, so the difference we will just see right now. Now, what I'm going to do, let's keep this 3A and 3B for later application. So let me consider, I'm taking a diversion now. Later I will come back to the correct derivation steps. So now consider the, now consider, I'm going to consider a derivative. Consider the derivative Now consider the derivative. Okay, I'm taking a derivative. See what derivative I'm taking. I'm going to take the derivative of dou u with beta. Okay, so derivative of the internal energy of the system with what? Beta. And beta is 1 by kt. It is depending on the temperature. So dou u by dou beta. Okay, so dou u by dou beta, instead of u I can take a mean of E. So that is dou by dou beta of the average of energy, right? Mean energy. So which I can substitute for that one. So from equation number 2, I'm substituting equation number 2. So I'm writing it is dou by dou beta of that equation number 2. What is that? That is numerator sum over r e raised to minus beta er divided by sum over r e raised to minus beta er. So that is what you have to find out. Dou by dou beta of this. What you do is you have to, you can just use this one as something like the product rule or something like, okay, product rule or quotient rule, because beta is there